Okay, so, oh, this is the ore minerals one. Right, hold on. I am getting ahead of myself. Let's talk about ore textures, and I'll talk about ore minerals tomorrow. We'll see how we go. So this is just starting to get introduction to the main textures you'll see of the ore minerals. We've talked about the alteration, and this week we'll talk more about the actual ore assemblages, and then that'll lead into the following weeks. I guess we're going to have breaks in lecture. I haven't thought about that actually, now that I think about it. So there'll be there'll be a couple of weeks off, I think, because that was the intensive period, and then we'll come back and we'll start actually looking at deposit styles more specifically. So that's the plan. So we'll just continue. We'll just assume there's going to be a break in lectures, and that'll save a whole bunch of issues. So different ore textures help us interpret how the ore formed, and so we'll just briefly go through them. It shouldn't take too long, but there's more main common types, and as you probably aware, they relate to the different deposit styles. Massive sulfides, you'll come across this quite commonly. So it refers to ore textures where there's dominantly a sulfide mineral in there, and it's quite pervasively present. So some people might say greater than 50%. Anyway, it's sort of neither here nor there, but you'll commonly hear things like massive sulfides. And of course, they're quite common in things like volcanic massive sulfide deposits, surprise, surprise. So where you get a significant amount of sulfides within the deposit. But as is the case, they can form in pretty much any of the types of main ore forming processes. Volcanic, sedimentary, exhalative deposits commonly can be massive sulfides. You can get them in orogenic systems, and you can get them in magmatic systems. So the texture is just describing that you're getting a lot of sulfides. And yeah, that's a fair point. Remember that we use massive to describe textures in rocks to mean sort of large, essentially mean featureless. So just be wary that this massive is actually talking about essentially a volumetric term instead of a featureless texture. So they're commonly banded or massive, so as in they're just large proportions of sulfides. They might be brecciated or slightly more disseminated. The type of sulfides will depend on the deposit. So of course, things like a VMS or SEDEX probably going to have a lot of lead, zinc sulfides, whereas some magmatics might have things like chalcopyrite or things like that. They're very heavy and dense, and they're quite competent but brittle, because the sulfides are fairly brittle, and they can range grain size. So here's an example. This is a sample where we have pentlandite, so nickel sulfide. So it could be, in this case, it might be some sort of could be a magmatic immiscible fluid case or something like that. We have chalcopyrite in this goldy colour through here, and we also have pyrrhotite, so a variability of pyrite, a sort of commonly magnetic one. So we have all these sulfide grains intergrown in this sort of coarse, reasonably coarse, large volume deposit. So it'd be extremely dense and quite interlocking of these sulfide textures. Here's another one. This one's a banded case. So we have galena, a fairly light coloured version of galena here. We have sphaerolite, so we're going from lead sulfide to zinc sulfide here. We have pyrite, and we have chalcopyrite. sort of glittering gold colours here. The pyrite is a bit duller in this case. So the banding is quite variable, anywhere between 3 to 5 centimetres. So we can actually form banding in different sulfides instead of them all intergrown together. We might get net textures. It's quite impressive. So this is usually during a crystallization from a silicate, out of a magma, and the sulfides might be interstitial. So here we have nice bladed pyroxene. It's forming this sort of coarse network intergrowth, and interstitial to it we have the later pyrrhotite that's formed between those grains, because it forms later in that igneous system. Remember, usually the metals are one of the last things in the magma commonly, and so they've crystallized after the pyroxene and they've filled up the leftover space. So that can be described as a netted texture. The other common case is broadly disseminated ore, so that just means it's spread out. And it's scattered through the host rock. This could be replacement or is just their own minerals that are formed. These are quite common for most systems, and particularly for things like gold, copper, in those magmatic systems, they're commonly as disseminated ore bodies. So we have to be careful though, because sometimes it can, things like lead and zinc, we commonly like them in massive sulfides to get the grade that we want. So something like gold, of course the grade margin is much smaller, so disseminated ore can be okay. So here we go. We see it's a bit more scattered here. This is chalcopyrite with these goldy coloured inside a monzodiorite, so probably some sort of porphyry or hydrothermal deposition here. It's occurring in the host rock but not in the veins. Okay, so it's probably fluid might have precipitated through and replaced minerals in the host rock or created those sulfides. So that's quite a distinct disseminated ore texture. Here's a breccia. So all minerals might be precipitated in the cement of the breccia. So remember, breccia, we're fragmenting the rock, but we have to somehow bind all those fragments together. So that is usually something that's related to the fluid. In a hydrothermal system, the fluid precipitates things out to act as cement, and it can be the form of ore minerals. So in this case we have bornite is precipitated in the cement of this altered diorite. But it's also disseminated as fine grains and aggregates in the altered rock. So you can sort of see bits and pieces through this host rock. So that fragmentation process has actually enabled some of that fluid to penetrate the host rock as well. Okay, vein. This is something we're getting quite comfortable with. So this is when the ore mineral is precipitated from that fluid directly in that vein. So in that void space, if you like. So very common ore mineral system. And then you're going to get it with a gangue mineral, could be quartz, most commonly quartz, could be calcite. This is commonly where you get gold. So most gold is in the vein, and commonly you can't see it. But in this case we've got chalcopyrite and bornite. Okay, here's another type of veins. They can be slightly more complicated. This one looks a bit layered. And it could be several successive flushes through the same fracture network, and you can get this sort of banded texture as minerals deposit at different times. The other time you can get it is because a vein, commonly the crystals are either crystallizing from the edge in, that's the most common, sometimes they crystallize from the center out. So you might get some crystallizing out and then a new fluid, and they'll crystallize on top. So you can actually get a sort of sequence of events, if you like, about thinking about which ones have deposited earlier. So in this case, we have pyrite, gold, and silver is deposited in the veins, and they give the bands this dark colour. And then we have brown bands of sphalerite. In the good times, instead of the vein being full of quartz, we can get what we call bonanza sort of grade, where it's just fantastic. In this case, it's just gold, so the whole vein is gold. So if you come across that, that's happy days. That's what you want to be hitting. So yeah, but chances of finding it can be difficult, I guess. Here's another vein. This is like a sheeted vein, and we're sort of in this photo where, like, if we're looking down at the vein as a sheet, we've got one half of the vein and we're looking inwards from one side. So the black mineral here is cassiterite. It seems to be intergrown with quartz. There's some staining here of the sulfides, which is very common as they oxidize. In this case, it's a mineral called jarosite. It forms after oxidization of pyrite. And so what's happened here is we've actually lost a lot of that quartz in that vein, probably when it's been broken open. This is the host rock here, which is actually a highly silicified metasediment. And what's been left is the cassiterite. But it gives you an idea of, in this case, a sheeted vein. You can have quite a large amount of ore minerals within there. Cassiterite is very resistant to weathering, and it's a heavy mineral, so it sticks around longer than some of the other examples. Here's quite a nice vein structure. We have sphalerolites cutting through a strongly altered andesite. And this is the case where you can start to get that timing relationship, where we have the sphalerite crystallized on the edge. You can see that we get these nice bands, and then the vein is actually crystallizing this way, and then we actually have another stage of a bit of sphalerite deposition and maybe some more quartz. And the vein's growing inwards from the outskirts in this case. So we're getting growth this way, going this way, and growth going this way. So the sphalerite was the early crystallization product, and then the quartz was mainly later. Okay, vugs and infills. This is just another example of you have a void space. So remember that things like vugs, these cavities, and they can be lined by crystals. They keep, in a granite, you typically get these spaces when they're very close to the surface, because the gas starts to dissolve and expand out, so you're left with bubbles. And the other thing about that is that it's usually the last little bits of the melt or the liquid, and so they're commonly enriched in metals. And so the metals might just go, okay, things are changing, I'll crystallize into that void space. So you might get molybdenum, it's quite common. Sometimes you get gold and silver, and they just form in these vugs or myrolitic cavities. And so again, they're commonly dominated by quartz and calcite. Okay, supergene textures. So, do we know what a supergene is? Yep. Okay, so we're fairly comfortable with it, what that means. So we have this chemical weathering. We can also get hypergene minerals that are like the original ones, so chalcopyrite, borite, sphalerite, pyrite, the things that haven't been oxidized in the top of or leached. And then they break down to form these secondary ore minerals, things like chalcocite, malachite here is nice greeny malachite. The blue is azurite. So we've got these secondary copper minerals. They're reduced in sulfur. And then we get these sort of textures where we have replacement of azurite and other secondary minerals. We might have some carbonate floating around. These supergene rocks are very friable. They'll break up easily. And a lot of their distribution is how the water is actually leaching through that rock and changing the chemistry, and we're removing a lot of mobile elements, and we're left with a lot of these metals, especially like copper. So they're quite common. Okay, replacement textures. So this is when we're replacing the original rocks, much like a pseudomorph, with an ore mineral. So they commonly indicate an epigenetic ore system, i.e. the ore formed after the rock. So it's, it's a timing feature. And they're quite common in many environments. In this case, we have chalcopyrite in yellow, this one, and pyrrhotite, the brassy colour, are replacing beds and classed within a sediment. So this would be classic for like a sedimentary connate fluid system where we have the beds and the fluids moving through and depositing these metals. Okay, here's another case, and this time we have a conglomerate. So we have these clasts. They're quite happy. The clasts are silicified and have not been replaced by the ore. But we have the outscored, the cement has been somewhat brecciated and has been replaced by chalcopyrite to make up most of that matrix. Okay, sulfide bandings. So sometimes we might get these things in bands. This could reflect this original sedimentary sedimentary layering. So things that like Mount Isa, you commonly see the sulfides will follow the sedimentary beds. And there's been a long-standing debate about whether that's syngenetic or epigenetic, but we have a severely banded sulfide texture. Could also be a secondary texture in a metamorphic rock, so related to a foliation. So things like Broken Hill, maybe a lot of the sulfides have actually been aligned in association to deformation. So in this photo we have arsenopyrite occurring in bands. There was probably a sedimentary rock, but now it's a chloride schist. So we can have to work through about using different geological relationships to decide, did the sulfides exist before it was metamorphosed or did they exist afterwards? So we had to do those standard sort of geological reasoning. Stringer zones. These are sort of elongate occurrences of ore minerals, so they're occurring all in a line. It might indicate a former fluid pathway that's now collapsed and we're just left with the ore minerals. And so they can usually dominate by quartz as well as sulfide minerals. And they can be interconnected or they might be slightly irregular depending if that vein has collapsed or is still present. They can be economic grade, but they're also good clues to where the massive sulfides might be, where you've actually had more pervasive fluid flow for the metal deposition. So here's some examples. We have these sort of chalcopyrite or pyrrhotite forming these sort of network textures. We can see down the bottom here, you have these little vein structures, and they start to give way to areas where we see higher grades of ore minerals or sulfide minerals. So you can sort of envisage that these structures are the same as these ones. So that's the idea. The vein is either, in these cases, all nicely chalcopyrite or pyrrhotite, or in this case arsenopyrite, but sometimes it's other gangue minerals. And so we call these stringers because we don't really have that defined vein structure anymore. We just have ore in a sort of network structure or texture. So that's all I have to say about ore textures. So have we got some questions? No, it's pretty straightforward. Not meant to be too crazy. Yeah, so I'll just stop this guy.